Okay, so this is lesson 21. And what we're going to focus on today is we're going to focus on the intersections of three planes in R3. Okay, so let's recall that so far we've done two lines. Okay, we've done a line and a plane, and we've done two planes. Okay, and we've seen all the different scenarios that can occur when we look at these intersections. Okay, one thing that was interesting about the intersection of two planes was that there was no way for two planes to intersect at one point for there to be a unique answer. But I don't know that that's too surprising, because when you think of solving two equations and two unknowns, or if you're looking for two unknowns, we usually say you need two pieces of information to solve for two unknowns. In other words, two equations. Okay, here we had two equations with three unknowns, so maybe it's not so surprising that we weren't able to solve for one unique solution. So presumably, if we consider three planes, will we have enough information? All right, so what I'm going to do is I'm going to give you a few minutes to take three pieces of paper or three pieces of cardboard, and I want you to try to come up with all the possible scenarios that you could have when you're considering the intersection or lack of intersection of three planes. Okay, so as an example, when we had two planes, they could be coincident, the same plane, they could be parallel and distinct, or they could intersect in a line. So you had three possibilities. Or the line, two lines, you had four possibilities. So take a few minutes and see how many scenarios you can come up with. All right, and we'll be back in say 2 minutes. Okay. All right, so let's get some ideas here, and hopefully we can get all possible scenarios. So who wants to start us off? So let's try to go as quickly as possible. You tell me how these things interact with each other. Okay, all three are parallel. So can you be a bit more specific? Because I feel as though there's more than one possibility when all of them are parallel. Can we be a little more distinct? Okay, so we can have that all three are parallel and distinct. Okay, good. What else? What else happens? So let's stick with this idea of the being parallel. They could all be coincident. So in other words, they all represent the same plane. Okay, let's think of other scenarios we could have with parallel planes, or at least some of them being parallel. So far, we have all parallel and distinct. We have all coincident. There you go. You could have two of them that are parallel. Okay, let me try to get that. Okay, and then what if they're parallel and distinct? And then you've got some third plane that's not parallel. Is there any intersection? Okay, the answer is actually no. Because remember, when we're talking about intersection, they have to all intersect at that point. So in this scenario here, is there any points where they're all intersecting at a particular point? And you realize that no. Okay, all right. But then what if you have two of them that are not just parallel and distinct? What if they're parallel and coincident? Do you have intersections here? Do they all intersect? And you realize, and what is that line of it? Oh, sorry, I guess I just gave it away. Okay, we see that we have a line of intersection. All right. So far, it looks like we've got four scenarios. I feel as though there's a fifth one. Exactly. It ends up just being like the intersection of two planes. Okay. I feel as though there's maybe one more scenario where you have parallel planes. There's one we haven't mentioned, and I'm kind of creating it here. What if you have two that are parallel and coincident, and a third one that's parallel and distinct? Are there any intersections here? And the answer is no. Okay, so we're starting to see already we're up to 5 scenarios. Okay, and that's just with scenarios where we have planes that are parallel to each other. So did somebody find any scenarios where the planes, where none of them were parallel to each other? Well, is it possible for these three planes to intersect in a point? Would you like to reassess your answer? And this is where we see that you can have three planes intersecting at a single point. You see this point right there is the one and only one point where they intersect. Okay, so this idea that if you're looking for three unknowns and you have three pieces of information, in other words, the equations of these planes, because the point is on each of the three planes, that you can find a single solution. Okay, were there any other scenarios that you found?
Could you also have the three planes sort of intersect at a line? So like, yeah, you could.
Maybe something like this?
Yeah.
There you go.
Yeah.
What if they create, I know it's hard to see here because the planes aren't going through, whoops, okay? But this is what we call the star formation, okay? Because if you can imagine that these planes keep going on the other side, you almost create a star or an asterisk. But you see here that the three planes, none of them are parallel, but they intersect in a line, okay? And is there another scenario? I think there's one more that I almost gave away. What if you have something like, I feel like I'm making a house of cards here. What if you have something like this? None of the planes are parallel. Are they intersecting? All three in the same spot? No, but it looks as though they're forming this sort of infinite triangular prism. Okay? So, if you count those up, we had 8 different scenarios. Okay? Let's take a look at them. And again, let's start by focusing in on the ones with the parallel planes. Because if we decide to work, or we're working with Cartesian form for the equations of these planes, well, if all three are the same, who can tell me how I should be able to just tell by looking at the equations that they're three coincident planes? Who can explain to me? And this is probably easier to explain in, with your voice instead of typing it out. This is a little long. So how could I know just by looking at a system of equations and say, oh yeah, these three planes are all coincident?
They would be just sort of, oh, go ahead, sorry.
Yeah, one of you pick, doesn't matter who it is. Who was that? Samia, I think. Go ahead.
Okay, sorry, I was saying that they're essentially scalar multiples of each other. So if it's in the Cartesian form, for example, the values should be like multiples of each other. So the A, B, C, and D values.
There you go. So first of all, if they're all parallel, you notice that the normal vectors are parallel to each other. But if they're all three going to be coincident, it means that also the D values. Now you'll notice here, and you'll see in a couple of days why I'm going to start putting the D value on the other side of the equation. Perfectly valid. Okay. In order for them to all be coincident, not only do the vectors, the normal vectors have to be parallel, but the D values have to differ by the same amount. So here we see, look at the normal vector here. It's 2 times that of the first one, and so is the D value. It's 2 times that of the first one. If you take a look at this one here, it's 5 times the value of the first one, or 2.5 times the value of the second one, and so is the D value. Okay, so you should be able to look at a system of equations like this and say, oh yeah, there's infinitely many solutions, and it's essentially all the points on this plane. Okay, what would be the only difference in this scenario? This one should look very similar. What would be the only difference in scenario 2 when you looked at these equations? Don't think too hard here.
2 of them would be like the ones that were coincident, but then one of them wouldn't have one, like the D value wouldn't be a multiple of either of the other 2.
There you go. So if I take a look,
you have the same. Sorry, I explained that badly.
No, you said it perfectly. Because here, take a look at the first and the third. You notice they're the same. These two, 1 and 3, are scalar multiples of each other, whereas number 2 is still parallel to these other two planes, but the d value doesn't have the same factor. You know, here the normal vector is twice number 1, but this d value is not twice number 2. And similarly, when you have 3 planes that are parallel and distinct, what you're going to see are 3 normal vectors that are all parallel to each other, but the d values are not scalar multiples with the same factor. You know, 1 is not 2 times 3. Negative 15 is not 3 times 5. Okay? So what I'm trying to get across here is similar to the intersection of two planes. There's certain scenarios that you shouldn't have to do any algebra for, other than checking whether something's a scalar multiple. Okay? And in fact, even if you take a look at this one here, as soon as you see that two planes are parallel and distinct, you know for certain there's no intersection, because planes 1 and 2 can't intersect. Okay? Now, if they're asking you for the geometric interpretation, well, here, again, I look at planes 1 and 2, and I see that the normal vectors are parallel, but the d values don't have the same factor between them. Okay, so parallel and distinct. And then number 3, I look at the normal vector, and it's not parallel to the other two. So I know that this is the geometric interpretation: 2 parallel and distinct, and 1 not parallel. You know, if you kind of take this and flip it around, you know, it kind of looks like a not equal sign. All right. The last one in this category is really the only one where you're going to be doing any work, because as somebody said, if I have 2 of them that are parallel and coincident, and then the third one that's not parallel at all, well, we know what happens when we have 2 non-parallel vector planes. They intersect in a line. So essentially what you're going to do is ignore, you know, this one here, and you're just solving the intersection of these 2 planes, just as we did before. Okay? So when it comes to scenarios where there's at least 2 parallel planes, in most cases you don't have to do any algebra at all. And in this last scenario where 2 are coincident and 1 is not parallel, you're just solving what we've already solved before, which is the intersection of 2 planes. Okay? So are there any questions on these first 5 scenarios? Sorry about that. No? Okay. So what we're going to be focusing in on in terms of doing some algebra, okay, are these 3 scenarios. Okay, and you'll notice in these 3 scenarios, there are no parallel planes. Okay, so we saw the one where they intersect in a line. We saw the one where they form that triangular prism, and then that one scenario where they actually intersect at a particular point. Okay, so this is where we're going to put our focus on. One thing I do want to talk about, though, is that there's
I had a question.
Oh, yeah.
Okay. For the each option there, right? The one of the planes doesn't necessarily have to be perpendicular, right? Because from the diagram, I can see that the angle is not. For number 8, the last one.
Yeah, nothing has to be perpendicular. Yeah. Okay. So in fact, if I look at this, you know, I can definitely create an example where, you know, let me try to see how I can get this to work. I don't know, something like this, you know, none of them are actually perpendicular to each other, but they intersect at the point. Okay, so no, they don't have to be perpendicular at all. Okay, good point. Okay, so like I was saying, these 2 here actually have something in common that is different from this scenario here. Okay, and I think it might be easier to look at the physical model. So if I take a look at this scenario with the three planes forming a triangular prism. Okay, okay. If I were to, I'm going to try to place it here. Can you see that in this case here, I can, see if I can get them to stay, I can take a cross section. And what would it create if I looked at a cross section, if I looked at it straight ahead? Do you notice how it creates a shape? It creates a triangle. Okay, let me see if I can get something a little better. Okay, now what's interesting about the fact that I can create a cross section that includes all three planes is I want you to consider the normal vectors to these planes. There's one normal vector. There's another normal vector. There's another normal vector. There's something special about how I can draw these normal vectors to these planes. Okay, so take a look at this scenario. Very similar to the intersect and align scenario. I wish I had thought this through a little better. Okay. Sorry about that. I'm going to do my best here. Let's say they intersect and align. Okay. Look at these normal vectors. There's something they have in common that is different when I consider the normal vectors when there's a single point of intersection. There's one normal vector, there's another normal vector, and here's the third. Does anybody see a difference between this scenario and the other two scenarios that I just looked at? Okay, again, not ideal to look at it through what do you call that, a camera. But notice how there's something different about this scenario. Okay, and that's when you realize that when you've got those first two scenarios, it's possible to have the vector, the normal vectors, all lie on the same plane. Okay, in fact, here I can show it here. There, there, and there. You see how I was able to place the normal vectors all on the same plane. Whereas when I have the intersecting in a point, there's no way to press, because if there's one normal vector, there's another normal vector on the same plane. There's no way that the third normal vector cannot be on the same plane. Okay, and this is actually going to be helpful for us. Okay, and what I'm going to do here is show a cross section. You see how when I've got, so this represents, you have to imagine the planes are coming out of the paper. When you have them intersecting in a line, okay, you can draw a cross section of it. When they intersect as a triangular prism, you can draw a cross section of it. In other words, you can also draw the normal vectors all on the same plane. We say these normal vectors are coplanar, whereas when they intersect in a point, there's no way for these three vectors to be drawn on the same plane. Okay, so how can we use this to our advantage to distinguish this scenario from the other two? So what I want you to think about, okay, I want you to think about how you might use some maybe useful operations on these three vectors that would allow us to determine when three vectors are coplanar and when they're not coplanar. Okay, so is there some operation I could perform to show that these three vectors have to lie on the same plane or won't lie on the same plane? Okay, now for now, we're just going to stick with three non-parallel vectors. We'll assume the vectors are non-parallel because we've dealt with all the situations where there's parallel vectors. But is there an operation you could perform that would distinguish this scenario where all three vectors are on the same plane and that scenario where the three vectors are not on the same plane? So I'm going to give you a minute to think about that. Okay. Okay, so we're back. And there's actually, by the way, two ways in which we can do this. There's an easier way and a longer way. Okay, but let's see what ideas. Did anybody come up with some ideas as to what operations I might use to show that three vectors lie on the same plane or do not lie on the same plane? So let's, you can even start, let's go through our operations, Is there a way to use vector addition to do that? Okay, so now here, somebody's suggesting cross product and scalar projection. Okay, so let's think about that. Well, I know to take a cross product, I'm only working with two vectors. So let's say I take the cross product of two vectors. What's special about the vector that we get? It's perpendicular to the original two vectors. So, let's wait for it to unfreeze. So if I do a cross product between two of the vectors, I know it's going to give me a perpendicular vector. Well, somebody's suggesting, oh, well, wait a minute. If this third vector is on the same plane, what is the relationship between this third vector and that cross product that you just found? What would have to be the relationship? They would have to be perpendicular to each other. In other words, the dot product would have to be 0. Whereas if this third vector is not on the same plane, then what can we say about the dot product between the third vector and the cross product that we just found? Well, I wouldn't necessarily assume it's greater than 0. It could be less than 0, but it definitely won't be equal to 0. Exactly. Okay, and this is what we're going to use. Now, if you remember, I made reference a while ago to this idea of triple products. Okay, and in particular, the scalar triple product, which is where you take a cross product followed by the dot product, and it's a valid operation. This is now where we're seeing the usefulness of it, that I take the cross product of any of the two vectors, and then I dot it with the third. If it turns out that the dot product's not 0, I know they're not coplanar, whereas if the dot product is 0, they must be coplanar. Okay? So what you can do is before you even start solving, okay, you could first take the scalar triple product of the three normal vectors, and if it's not equal to 0, you know that it intersects in a point. Now, you might sort of think, well, wait a minute, if I'm going to do the work anyways, what's the point of checking? And you would be right. But in some circumstances, we're only interested in scenarios that give us a single point of intersection. So that's why you would be worth checking, so that if the scalar triple product is 0, you could just say, well, I know there won't be a single solution. All right? So let's take a look now at some examples here. By the way, before we're going on, might as well talk about, there's actually another way in which we can show that three vectors are coplanar. And this is something we've done. So what do you think is something else you could do to show that three vectors have to lie on the same plane? I'll give you a hint. It doesn't use a product. It actually uses vector addition and scalar multiplication instead of using products. How could I show that these three vectors have to lie on the same plane? Does this give you? There you go. There's another way to do it. Is if you can show that the third vector can be written as a linear combination of the other two vectors, then they must lie on the same plane. Okay? In other words, if these two can act as basis vectors, so if this third vector is on the same plane, when you take a linear combination of the first two vectors, it can be written as the third. Whereas if this vector is not on the plane, that would be impossible. That just takes generally a little more time. So that's why, we're going to stick with using the scalar triple product instead of doing it in that alternative way. Okay, but there is that available to you. All right, so let's take a look now at some examples, and we're actually not going to do any solving today. We're going to start that tomorrow. Okay, so let's just make sure that we understand what I'm saying. So we say if our three normal vectors, n1, n2, and 3, okay, are, let's just say, non-zero, non-parallel vectors, okay, then if the scalar triple product, and by the way, it doesn't matter what order you do this in, if this is equal to 0, okay, we have that the vectors are coplanar. And then if n1 dot n2 cross n3 is not equal to 0, then vectors not coplanar. Now, in terms of finding intersections of lines, that if you know a priori that your normal vectors are non-zero, non-parallel, as soon as the scalar triple product is 0, you know that the three planes intersect at one point. Okay? Whereas if you take the scalar triple product and the vectors are coplanar, you have two possibilities. Okay? Possibility 1 is what I'll call the star formation, or possibility 2 is the triangular prism scenario. Okay? So what we're going to do now is we're going to take a look at some examples, and notice how I'm asking the question. I'm not asking you to determine the intersection. I'm just asking you for the nature of the intersection. Okay? So what I want you to do is I want you to work on these here. You shouldn't be trying to solve these systems of equations. We're not trying to find the actual intersection of these planes if there is an intersection. I just want you to use what we talked about. So are there any planes that are parallel to each other? Can I use that to make a determination of what's going on? And if none of them are parallel, how can I use the scalar triple product to help me determine what scenario I've got? Okay? So I'm going to give you maybe 6-7 minutes to work through these. All right, so we're back here. So let's talk about the first one. Should I be taking the scalar triple product in this case? So if we're looking at 3. Okay, so Samya, you're saying no. Why no? Don't I want the nature of the intersection? Ah, there we go. So the first thing you should be taking a quick look at anytime before you start doing an intersection of three planes questions is definitely take a look at the three equations. And we notice that the first and the third are definitely parallel to each other, but not only are they parallel, they're actually coincident, because the normal vector here is twice the normal vector in the first one, and the d value is also twice the d value there. So here, for part A, we have that 1 and 3 are coincident. Okay. And I take a look at number 2, clearly not parallel. So what is the conclusion if I have 2 coincident planes and one that's not parallel? So maybe somebody else can give me the conclusion that we can make here in this scenario. There you go. That they must intersect in the line. Okay, so 3 planes intersect in a line. Now, of course, when you're actually solving for that line, you're not going to work with all 3 planes because you know that the first and the third are identical to each other. So you might as well just work with the first and the second. And you would solve it the way you solve any intersection of 2 planes. Okay? So let's take a look at number 2. Are any of these parallel to each other? Okay, you take a look, none of them are parallel. So this is where, you would start to look at other ways of determining the nature of the intersection. Okay, now, what I want you to think about as I'm doing these is that we have these 2 alternative methods, this idea of the scalar triple product and this idea of writing one vector or trying to write one normal vector as the sum of the other. Okay. The good thing about the scalar triple product is it's a little quicker. And usually what's most important to us is determining whether there's a unique solution or not. All right. But it has the disadvantage that if the scalar triple product is 0, then we have 2 possible options. Okay. The other way of solving, or determining whether 3 vectors are coplanar actually makes it easier to tell whether it's a triangular prism or a intersecting in a line. Because we're not really going to be spending much time just determining the nature of intersections, we're actually going to be trying to solve for them. I'm not going to spend time on that, but you should think about how you might use what we talked about earlier about writing one as a linear combination of the other 2 to help you identify the triangular prism versus the intersect in a line. But for now, let's just work on the scalar triple product. Okay. Now, it doesn't matter what 2 vectors. So, I wrote it as n1 dot n2 cross n3. Doesn't really matter the order. So let's use that order for this one here, but it really doesn't matter. You probably want to usually start, so if I have n1 is 1, 2, 1, okay, and 2 is 2, negative 1, 1, and then n3 is 3, 1, negative 2. Now, if I had to take a cross product, I'd probably work with these 2 here, okay? Whereas, if I want to follow the formula as given, I guess I could take it. In the end, doesn't matter. So let me take these 2 here. But I think next time around, I'll probably just pick whatever's seems easiest. So if I take 2, negative 1, 1, and then 3, 1, negative 2, and let's find the cross product. Okay, so what do we have? We have negative 2 minus 1 is negative 3. Then we have 3 plus 4 is 7. Okay, make sure you're checking my arithmetic. And then here we have 2 plus 3 is 5. So once I find, oh, yeah.
The first 2 is positive.
The first 2.
Negative 1, like for.
Oh, 2 minus 1, good show. Thank you. That's why I asked you guys to look at my arithmetic. Good catch. So here this is going to be 2 minus 1, so that just should be 1. Thank you very much. Okay, and now let me dot it with the vector I didn't use, 1, 2, 1. And what do we get? We get 1 plus 14 plus 5, which is equal to 20, which is not equal to 0. So what's my geometric interpretation here? If I have 3 non-parallel vectors and the scalar triple product is not equal to 0, what can there you go. These 3 must intersect at a point. Okay, and I'm just going to repeat this for the other 2. Okay, so here, in this case here now, I'm going to work with the easier ones first. It's just easier to take this cross product first. So I'm going to start with, 1, 1, 2, and then 1, negative 4, take the cross product of these two. Okay, -4 plus 2, -2. 2 plus 4 is 6. -1 minus 1, -2. And now I'm going to dot it with the third normal vector, and I get 3, 5, 12. So let's see what we get. We get -6 plus 30 minus 24, and that's equal to 0. Okay, so our conclusion is that it's either intersect in a line or we have the triangular prism. Okay, so this is the inconvenient part about doing the scalar triple product, is that it doesn't distinguish between these two. It's one or the other. So like I said, I'm not going to do it because it's really not going to be a focus, but especially if you're, I always say, if you're someone who's, going to be taking linear algebra courses in university, try to figure out how you would use that alternative method of writing one vector as the scale, as a linear combination of the other two, how you might use that to distinguish whether this represents intersecting in a line or triangular prism. And if you want to send me an email to check your answer, I'm happy to do that. Okay. And similarly here, D, let's see what happens. So again, I don't know. I'm going to say the first and the third look a little easier. So 1, -3, -2. And if you chose a different combination, hopefully you'll see that you still came up with something similar. Okay. And so let's see what we have here when I take the cross product. So this looks like -9 plus 16 is 7. -4 minus 3, -7. And this is 8 plus 6 is 14. Again, check my algebra there. And then let's dot that with the third vector that I didn't use, which was 1, 11, 5. 1, 11, 5. And let's take that. So what do we have? We have 7 times minus 77, 14 times 5, 50. So it's plus 70. And that's, look at that, equal to 0 again. Okay, so same as before. We have one of those two. All right. So for now, what I want you to get out of this lesson is, number one, to be able to distinguish all the different scenarios that we can have when we're considering the intersection of three planes. Okay. Understand that with the first 5 scenarios where there's parallel planes, you should be able to either give an answer right away, or at the very most, take this problem of intersecting 3 planes and turning it into a problem of intersecting 2 planes. Okay? That the real work is going to come with these 3 scenarios. Okay? And if you did want to do a check beforehand, you have access to this scalar triple product to determine whether the normal vectors are coplanar, in which case it's one of these 2 scenarios, or they're not coplanar, in which case there has to be one and only one point of intersection. And what we're going to start focusing in on tomorrow is how to solve for these intersections. But as I think I've alluded to, while we're going to start with this geometric problem of finding the intersections of 3 planes, where this really becomes useful is more this idea of solving systems of equations. Okay? In other words, how do we solve 3 equations in 3 unknowns? Okay? And in particular, what we're going to focus on is, well, while these things represent planes geometrically, we consider these to be linear equations. Okay, from an algebraic perspective, okay, we still call these linear equations because essentially none of the variables are being squared or being square rooted or having any other operations on them. It's just a linear combination now of these three variables. Instead of a linear combination of two variables or two vectors, these are all linear combinations of these three variables. Okay, so that's the end of this lesson.